An intuitive introduction to generative adversarial networks, GANs. Explaining the magic of GANs in computer vision. Consider an art forger trying to create fake paintings of Leonardo da Vinci and a detective who is trying to identify if the painting is a real or a fake painting. Initially, the forger may not be great at creating replicas of Da Vinci's paintings, and it might be easier for the detective to spot the fake paintings. With time, the forger learns the key components that the detective checks in the painting to classify it as a real painting or a fake painting. Similarly, as the detective sees more of the real and the fake paintings, the detective is able to learn the finer details required to differentiate between the two. Eventually, the forger will learn the tricks so well that the forger will start fooling the detective into believing that the fake paintings are the original paintings of Da Vinci. Now we can say that the training for the forger is complete. This is exactly how the GAN works. Generative Adversarial Networks, or GANs, is one of the amazing innovations of the decade that has led to many state-of-the-art products in the recent times. GAN was first introduced in 2014 by Ian Goodfellow et al. In the paper Generative Adversarial Networks. Since its inception, there have been several variants of the GANs serving different needs. Generative Adversarial Networks, GANs, is a deep learning-based generative model that discovers underlying patterns in the input data and generates new samples from it. Don't get intimidated by the name or the definition. Once you reach the end of this video, you will be awed by its simplicity. The basic GAN architecture has two neural networks, the generator and the discriminator. Once the generator is able to create data that can fool the discriminator into thinking that it is real, then the model training is complete and the generator is trained to create good fake data. Deep Convolutional Generative Adversarial Networks, or GANs, is one of the popular approaches of GAN that is specifically used for image data. The DCGAN adds convolutional layers between the input noise vector and output image in the generator. In addition, the discriminator uses convolutional layers to classify the actual and generated images as real or fake. GAN uses two neural networks internally, the generator and the discriminator. The generator network generates an image from a latent vector, noise vector in the case of DCGAN, and is a type of unsupervised machine learning. The discriminator network classifies an image as real or fake and is a type of supervised learning, as the labels, real/fake, are used to train the models. Now moving to the working of GAN. During training, GAN takes in two inputs, random noise data and an input data that is not labeled. Using these two inputs, it generates data that resembles the input data. Since all the inputs to the GAN are unlabeled, GAN is a type of unsupervised machine learning. In our forger detective story, this is how the forger learns with every iteration. The generator architecture is a neural network which takes in the noise input vector and converts it to an output image, in the case of DCGAN. Here is an example of the generator architecture picked from the DCGAN paper. As seen in the below architecture, the input to the generator is a noise vector Z of size 100. This is first projected and reshaped to 1024 by 4 by 4 data, followed by convolution layers of 512 by 8 by 8, 256 by 16 by 16, and 128 by 32 by 32. Finally, this is fed into the output layer to generate a 64 by 64 RGB image. Here is how the detective learns with every iteration. Discriminators are simple binary classifiers that classify the input data as real or fake. In the case of DCGAN, the discriminator is a convolutional neural network, CNN, that does a binary classification. The input to this CNN is an image and the discriminator needs to classify it as a real image or a fake image. As discussed earlier, there are two neural networks involved in the GAN architecture, and hence there are two types of losses that needs to be backpropagated during the model training step. The discriminator classifies both the fake data from the generator and the actual data. When it classifies the generator data as fake or the actual data as real, then it is doing a good job, otherwise it is misclassifying the output and the model needs to be retrained for this input. Hence, when the discriminator classifies a fake image as real or a real image as fake, it is penalized with the discriminator loss, and this loss is backpropagated through the discriminator network to update the weights and biases. Note that the generator weights and biases will be frozen while the discriminator is being trained. The role of the generator is to create an image from the noise input, and it does not have any labeled information on the type of output expected. Hence, the generator uses the output of the discriminator to update its network parameters. If the discriminator misclassifies the image generated from the generator as a real image, then the generator is doing its job, but if the discriminator can identify that the generated image is a fake, then the generator needs to be updated. Hence, when the discriminator identifies a fake image and classifies it as fake, then the generator loss is computed and backpropagated to the generator network to update its weights and biases.